Hi, in this video, we're going to take a look at Bayesian logistic regression. Okay, so in Bayesian modeling, what we've got going on is I have a prior belief about what's going on, and then I have some data, and I put them together to get, hopefully, a better model. Now, the prior, honestly, could be 100% of our model. We could actually do statistical modeling with the prior belief by itself. But in general, when we deal with our priors are higher dispersion, greater variance than what's practical. That we have an idea of the central tendency of a parameter, but we don't really have like the spread isn't as nailed down. So we go high on the dispersion to make sure we're not being like overly confident. Now, my opinion is that Bayesian statistics really should not be used that often. My personal opinion, you can disagree with me if you want. We've got 2 points of view, the frequentist statistics and Bayesian statistics. Frequentist, what we're going to do, we're going to take the data. The data is everything. The data is going to drive what's going on. And in my experience, most of the time, the data dominates what's going to end up happening, whether I do a frequentist or Bayesian model. Now, the Bayesian statistics, Bayesian approach is definitely very useful. It's very powerful. The times to use it, first and foremost, I would say when you have small data, your stakeholders want you to use it. Let's say, somebody just wants you to use this particular modeling, they feel comfortable with it. Another way is if, let's say I don't have as much data as I want, but I have a good amount of like subject matter knowledge on what's going on. So from previous experience that I could make a pretty good model without the data, then I can pull it all in together and get a very good Bayesian model going. The reason why I don't like Bayesian statistics is that it's computationally way more expensive. And honestly, it's a more complicated model. We have the potential of biasing our models. Now, there are things we can do to prevent bias, but those things that prevent bias, in my opinion, make it so that the prior isn't useful. So why would I bother with it? And so, it also just makes a more complicated model overall. And so my opinion is that we should avoid Bayesian, but it's still a good tool. I've used it successfully in the right situations professionally. So, it definitely has a place. It's very powerful. And there's some things that you can pull out Bayesian models that you can't get from frequentist models, that you get a more complete model, more complete representation of the situation. But usually that extra information is stuff that we really don't care about usually, but it's a good tool in our tool belt. All right, so Bayesian statistics, what this does, this enables us to take our prior knowledge and our observed data and put them together. And so the classic statistics approach does not incorporate our prior knowledge to the extent that Bayesian does. Classic statistics, called frequentist statistics, only uses the observed data and some assumptions, while in the frequentist approach completely disregards established knowledge. So, if I have a stakeholder that's been working in their field for 20 years, they know what's going on. They haven't, they know how things should look. They truly know their subject. The frequentist approach completely doesn't take that into account. It completely disregards it and proceeds forward as if no one knows anything. Now, that's good for not biasing us from anything, but you could just see that there's some stuff that's potentially lost by not using your subject matter experts. Right. So our established knowledge is going to be represented by probability distributions. And we're going to call the probability distributions our prior distributions. What's going to end up happening is I'm going to take my prior distribution, my data, fit the model, and then the new distributions that I get are going to be called the posterior distributions. So the posterior distribution, or excuse me, the prior distributions are combined with the observed data and the data's likelihood function to create new distributions. These new distributions are called our posterior distributions. Bayesian statistics use the posterior distributions to make inferences and predictions. Now, something that is really neat and really cool about Bayesian statistics is that we can, once I have a model and I get new data, I just go and I take my current model, I incorporate the new data and I update it. And so when I do this, I take my priors, I fit some data, I get a posterior. When I get new data, that posterior becomes the prior, and then I combine my data, I get a new posterior, I get new distributions. And so Bayesian statistics has this mechanism to continuously update our data as things progress. Now, if you think about the situation of data changing over time, year after year, this is a really good situation that typically what you'll see is that things don't drastically change. Even with COVID, things didn't change that much on a lot of data fields. That when I look back at data from 2019, 2020 at work, I do see a difference, but I don't see wild swings in my lane professionally. And so Bayesian statistics gives us a mechanism built in to be able to take, all right, I'm going to have that the old data, going to build a model, and then I'll go ahead and incorporate my new data, which may or may not have changed in distribution, to get a new up-to-date refreshed model. All right, so let's contrast frequentist statistics and Bayesian statistics. All right, frequentist statistics takes the point of view that the data is random and the parameters are fixed values, while Bayesian statistics turns this on its head and the data are the fixed values. So this is after I observe the data. Once I observe the data, it's locked, it's constant, it's fixed. And now the parameters have the probability distributions. Now, if you are a mathematician, if you have a stronger math background, we're going to be taking the point of view that the parameters are not actually random. When I say probability distribution, we're saying that they have a measure associated with them. And so small nuance, but it doesn't make that big of a difference for practitioners. Now, advantages of Bayesian statistics. I mean, the big one, the big, huge thing that makes this nice is that it incorporates established knowledge. I can look at previous papers, previous models. I can talk to subject matter experts and bring that in to get a better overall model. We can create a model with very little data. I mean, potentially, I could just use the priors and not even use any data whatsoever to do statistical modeling. I've never seen that actually done, but from a pencil and paper theory point of view, there's no reason why we couldn't. Bayesian statistics give us a more complete model, but unfortunately, that additional information is kind of esoteric and very mathy. Like when I say math, I mean like pure mathematician point of view, which is interesting for somebody like me, but typically on the job and application, the additional information isn't that useful. Bayesian statistics is extremely flexible, especially if you're doing something like RJAGs with Monte Carlo Markov chain. I've done this myself professionally, where I fit some very, very flexible models that I would not have been able to fit using a frequentist point of view because nobody went through and coded it. So I was in a situation where stakeholders wanted a particular structure for the model, but this was assuming things that nobody had ever coded this type of model structure for and this type of regression. And the easiest way for me to do this was actually go into RJAGs and do it as a Bayesian statistics model rather than a frequentist. Now, there are some major disadvantages of Bayesian statistics. First and foremost, Bayesian statistics is more complicated than the frequentist point of view. Also, it can take a lot more computational time to fit the models. I mean, a lot more. Also, by having the priors, we have to have a subjective decision. All right, so when I say I'm tapping into established knowledge, well, two different subject matter experts may have different priors that they would come up with. And so then it's a subjective call. And so, we're pulling in subjectivity into our models. Now, there are things that we can do to help protect ourselves from making bad decisions, but really, we're exposing ourselves to that risk no matter what we do. Also, the priors that minimize the probability of bias, so by basically having high variance, high dispersion, really, in my opinion, don't really enhance the information of the model. The priors are so vague that they don't really add to what the data gives us anyway. So what's the point of going through all this extra work? So like when we talk about Jeffrey's prior, I feel like it's just not worth bothering with. All right, so here's my advice. Avoid Bayesian models if you can. Bayesian models have more parameters, they're more complicated, harder to interpret, and they take a lot longer to compute. It's not so bad if I use a conjugate prior, but if I use a Monte Carlo Markov chain to fit it, it can take a long, long time. Like go leave the building, have a nice long lunch, go on a jog, come back, and it'll still be computing. Now for frequentist statistics, instead use frequentist if you can, but let's say your stakeholders want Bayesian model, then you're using a Bayesian model. If I have very little data, like really, really very little data, like it's not feasible to fit the model I need, then Bayesian model can come in and save the day. And also, if there's information that I can't get from a frequentist model that a Bayesian model would provide, then of course I'm going to use a Bayesian model. So Bayesian statistics has a very good solid place in modeling. I just personally don't prefer it. Now, if you can, use conjugate priors. So conjugate priors are basically, if the theory is right, if this works up with our subject matter knowledge, conjugate priors are basically selecting the right prior posterior likelihood combinations so that the math works out very, very easily, and I can fit things very quickly, very easily. And potentially, I won't have to use a Monte Carlo Markov chain. This will speed things up, keep things simpler. I don't have to worry about computation time. I don't have to worry about convergence. So for the most part, if you can, use conjugate priors. I find the best source of conjugate prior information is actually Wikipedia's page. It has some nice tables in there that lists the combinations. Conjugate priors are typically easier to interpret, easier to compare like different models between. They're computationally way faster, and they don't suffer from the problems of using a Monte Carlo Markov chain, like problems with convergence and iterations and other stuff. All right, so let's go ahead and start doing some examples. And so I'm going to go ahead and use the SA Heart dataset from the Elementary Statistics Learning package. Do some light data prep of converting to a dummy variable for a binary column. And I'm going to create a benchmark model, just standard, regular, old logistic regression, just so that we can compare to. All right, so now let's fit our Bayesian logistic regression models. And so by default, many of the prior distribution scales are multiplied by the standard deviations of the data. This can be suppressed with the auto scale parameter, by the way. So this is something that you can be mindful of if I want to control what's going on this front. You'll notice that in the examples, I leave things on default settings just so you can see what's up and how to start with it, and you can dig in deeper and read the help documentation if you want. But so here I'm going to take just the binomial family. I'm going to take the null prior, and I'm using the stanarm package, and I'm using stan glm for this, and I'm using the same formula as I had before. I had chronic heart disease, and all other columns are predictor variables on that. All right, and you can see that compared to the regular old generalized linear model, there's a lot more going on. I've got these chains going on for fitting. We have a warm-up. We have warm-ups, and then we have actual sampling going on. So we have 50% warm-up, 50% sampling. We have our elapsed time. These models take a lot longer to compute, so it's important for us to be mindful of how long this is going to take. For chain 2, going through something similar, and we have chain 3. And we have chain 4. We go through all these. So here I fit the model. And at the end of the video, I'll go through and compare the different models. Now, other priors that we can choose. So previously, I just left it on the default null prior. Now I'm going to specify that I want the normal prior. And so I'm not changing any of the parameters. I'll show how to change parameters in an upcoming one. But here I'm saying that the coefficients in my logistic regression model, that the prior distributions are normally distributed, and that we'll use that for the computations. And so we're just going through. You can see that if I don't tinker with the settings, it's going to repeat this over and over and over every single time I fit a model. Now, instead of normal, I could also use student's t distribution. And so here, bell shape, very similar to normal, but we have heavier tails. Very important distribution. So here we have more dispersion on the prior distributions. Now we can go all the way to degree 1 t and get the Cauchy distribution. So remember, the Cauchy distribution is the t distribution with 1 degree of freedom. And this is very important from a theory point of view, in that this distribution does not have an expected value. It also doesn't have a variance, or you would say it would have infinite variance, but it does not have an expected value. And it's such a spread out distribution, but still symmetric, still kind of bell shaped. And so let's go ahead and use that. So here what I'm saying is that the prior distribution for my coefficients is the Cauchy distribution. We also have the HS prior, where I just put that in. And there's a whole bunch of other ones I'm going to go over in a moment. Like HS plus is coming up next. Boom. If that's one you want to use. I have always used the normal distribution every single time when I've done Bayesian statistics professionally, by the way. All right, and so we can see that we got some warnings and some issues with this. This is something I just want to be mindful of. If I see problems with the model when I look at it, as I was going through the results and comparing different models, I would be quick to throw this one out. We have a Laplace prior here. Now here, there's the lasso prior. I've never used that professionally, by the way. We have product normal. All right, so let's go ahead and take a look at this, and let's go ahead and say that I want to actually specify some specific information about the distribution. So I'm going to go with a normal distribution, because by far that's the most common way to go. And I have from, let's say, previous model, or from a previous, like maybe an academic paper, a similar but different model, I have these are the coefficients from another model, or maybe they're the expected values of the posteriors from another Bayesian statistics model. And then here, I'm going to use this as my standard deviation. Now, something that's interesting about this is that this is, in effect, I'm doing transfer learning off of this. That if I have another model or pre-established knowledge, I'm using that to come up with these values. And in fact, I could use that as an entire model unto itself if I wanted to. I could actually start computing things very nicely. As I put auto scale to false. And so now what's going to end up happening is that the Stan GLM is going to combine the model that I have established as the prior model, as a Bayesian statistics model, it's going to take the data and it's going to combine the two and then give me a new model. And so let's go through and do that. All right, I'm going to go ahead and print that out. All right, so here we can see our formula, number of observations, number of predictors. And so here's the median of each of these. And so let's see how much it changed. All right, so I started with 0.007, pretty close to 0. And it's like negative 64. Wow, I mean, it's quite a bit of difference. So, or sorry, negative 6.4. The systolic blood pressure now has an estimated coefficient of 0. Tobacco has a coefficient of 0.1. Cholesterol 0.2. Adipose tissue of 0. And you know, and we can go down the line and just see what we've got for our variables. And you know, looking at this, I might want to consider removing some predictor variables after looking at these median coefficients. And we can see it here in another manner. Now remember that each of these parameters has a posterior distribution. And so that posterior distribution is a probability distribution. And what's going on is that, like for systolic blood pressure, I'm seeing that I've got an 80% interval that's like practically speaking 0. So maybe I want to remove systolic blood pressure from the model. Maybe not. We can see that here tobacco, that interval looks pretty tight around the estimates. Cholesterol isn't as tight as the other two, but it's still pretty tight. Adipose tissue, pretty tight around 0. I can't tell if there's a positive or negative on either side. Family history, all right, so family history has a little bit wider of a distribution. And so one thing I'm going to do when I look at these coefficients is I'm going to interpret the distributions of each of these to better understand what's going on. And that'll also help me spot maybe something wrong happened. Maybe I didn't specify a very good model for the data that I have. All right. And so we have our average posterior predictive distributions. And so we have a mean of 0.3, and then the interval is pretty tight around 0.3. Now here are my Monte Carlo Markov chain diagnostics. All right, so now let's go ahead and plot what's going on. So what I'm going to do, I'm going to take all the coefficients I have. So remember that when I did this, there was a whole bunch of coefficients that were generated by the Monte Carlo Markov chain. And this is in a way similar to having like a bootstrap approximation of the distribution. And what I'm going to do, I'm going to take all those Monte Carlo Markov chain generated values and put them into a data frame so I can plot them and compare them and better understand what's going on. And so I can see this, you know, so I'm using the gather function. So I'm taking the data frame, I'm taking it from wide to long. And now here, if I do as.data frame, I'm actually dropping several slots from the model. And I'm basically just keeping only that one, the Monte Carlo data frame. And then, you know, I'm just reshaping it to be in long format. And now I'm going to plot the histograms of each of these. All right, and so you can see we have all negative values over here. Here, there's a negative and a positive, but the distribution is almost completely. So the distribution includes 0. So maybe I want to consider removing that. And I've got some negative values on the left and positive. Maybe alcohol should be removed. Everything, it looks like it's, so here is 0. here is 0. So, there might be a few that, from a statistical hypothesis testing point of view, I want to remove. And, this gives me an idea of what the distribution is. All right, so now let's go ahead and compare the model prediction. So what I'm going to do, I've got all these models floating around in my workspace. I'm going to grab all of them. And so here, what this is the list of all objects in my workspace. I'm going to go and I'm going to take only the ones that are the stand GLM models. And so this is a regular expression for the beginning. So that caret is beginning, needs to be stand GLM. And then I'm going to use the get function to put them all into a list. Once I have them in a list, I'm going to go through and use the rstand-arm predict function. You'll notice it's different than regular predict. So they're not using the predict method. And then once I get those predictions, I'm going to bind everything up, or I'm going to take the column means to average out the values. And then I'm going to, for each of those, I'm going to go through and get a data frame. So I have tons and tons and tons of coefficient estimates for each individual model. And what this is doing is that this is averaging those coefficient estimates throughout. Here, I'm just cleaning up what I have. And now I'm going to go ahead and compute the area under the curve for each of the models. Now, area under the curve is a measurement of how well does the model perform at different levels of cutoffs. So when I say a cutoff of 0.5 for heart disease, no heart disease, it might be that I'm going to get way too many cases of true heart disease, or I might have too few. And what I could do is say, you know what, if our model probability is 0.75, I'll say they have heart disease, or maybe a model probability of 0.25 or higher, they have heart disease. I can adjust the threshold. AUC takes into account the full range of possible cutoffs and adjust the mistakes that we're going to make. So think about if I put the probability of saying heart disease at 0.75, there are going to be cases that I'm going to miss that I wouldn't have missed at 0.5. If I put it at 0.75, then I'm going to be calling that people have heart disease when they don't, compared to the 0.5 criteria. And so because of that, when I increase or decrease the cutoff, I'm introducing mistakes on one end or the other. And so AUC takes into account the full range of possible cutoffs. All right, and we can see that I've got 0.79, 0.79, 0.79, but all right, Laplace is a whopping 0.8, student T is 0.8, and the rest are 0.79. Okay, now what about that benchmark model? Well, the benchmark model ends up being 0.8. So they're all pretty tight with each other. So for the amount of effort that I went through and the computation time and figuring out what's going on and figuring out the priors, you know what? I ended up doing just as well if I would have just gone with a regular frequentist model. All right, homework. Take your data. Fit a Bayesian statistics logistic regression model, post it on the Canvas. All right, that's all I've got for you. Life is short. Do math.